right, hey everyone, welcome back. So let's continue our discussion today of reinforcement learning and MDPs. And specifically, what I hope you learn from today is how to apply reinforcement learning even to continuous state or infinite state MDPs. So talk about discretization, model-based RL, talk about models and simulation, and fitted value iteration is the main algorithm I want to lead up to for today. Just to recap, because we're going to build on what we had learned in the last two lectures, I want to make sure that you have the notation fresh in your mind. MDP was states, actions, transition probabilities, discount factor, reward. That was our example. V pi was the value function for a policy pi, which is expected payoff if you execute that policy starting from a state S. And V star was the optimal value function. And last time we figured out that if you know what is V star, then pi star, the optimal policy or the optimal action for a given state, can be computed as the argmax of that. Right? One thing though we'll come back to later is an equivalent way of writing that formula is that this is the expectation with respect to S prime drawn from PSA of V star of S prime, right? So when we go to, we have been working with discrete state MDPs with the 11 state MDP. So this is a sum over all the states S prime. But when we go to continuous state MDPs, the generalization of this, or what this becomes, is the expected value with respect to S prime drawn from the state transition probabilities, with indexed by SA, current state, current action, of the value that you attain in the future, so V star of S prime. Okay? And then we saw the value iteration algorithm. We talked about value iteration, policy iteration. But today, we'll build on value iteration. But the value iteration algorithm uses Bellman's equations, which says, take the left-hand side, set it to the right-hand side, right? And for V star, if V was equal to V star, the left-hand side is equal to the right-hand side. That was, oh, I'm sorry. It's missing a max there, right? If V was equal to V star, then the left-hand side and the right-hand side would be equal to each other. But what value iteration does is an algorithm that initializes V of S to 0 and repeatedly carries this update until V converges to V star. And after that, you can then compute pi star, or find for every state, find the optimal action A. Okay? So because we're going to build on this notation and this set of ideas today, so to make sure all this makes sense, right? Any questions about this before we move on? Okay, cool. All right. So, okay. So everything we've done so far was built on the MDP having a finite set of states, right? So with the 11-state MDP, S was a discrete set of states. Last time on Monday, I think someone actually asked, well, how do you deal with continuous states? So we'll work on that today. But let's say you want to build a, let me draw a car, right? Let's say you want to build a car, maybe a self-driving car, right? The state space of a car is, let's see, I'm gonna, instead of taking my artistic side view of the car, if you take a top-down view of a car, right? So this is from the satellite imagery, top-down view of a car with two wheels, car heading this way. How do you model the state of a car, right? Well, a common way to model the state of a car that's driving around on planet Earth is that you need to know the position, right? And so that can be represented as x comma y. Two numbers represent, longitude or latitude or something, right? You probably want to know the orientation of the car, right? Maybe measure it relative to north, what's the orientation of the car? And then it turns out if you're driving at very low speeds, this is fine. But if you're driving at anything other than very low speeds, then we'll often include in the state space also the velocities and angular velocity. So x dot is the velocity in the x direction. So x dot is dx dt, right? Oh, it's the velocity in x direction. Y dot is velocity in y direction, and theta dot is the angular velocity, the rate at which your car is turning. Okay, and it's sort of up to you how you want to model the car. Is it important to model the current angle of the steering wheel? Is it important to model how worn down is your front left tire as opposed to how worn down is your rear right tire? So depending on the application you are building, it's up to you to decide what is the state space you want to use to model this car. And I guess, and if you're building a car to race on a racetrack, maybe it is important to model what is the temperature of your engine and how worn down is each of your four tires separately. But for a lot of normal driving, this would be sufficient level of detail to model the state space. Okay. But so this is a six-dimensional. So this is a six-dimensional state space representation. Oh, and for those that work in robotics, that would be called the kinematic model of the car, and that would be the dynamics model of the car, right? If you want to model the velocities as well. Or let's see. Actually, all right. How about a helicopter? Right. I don't know. How's this a helicopter? All right. The state, how do you model the state space of a helicopter? Helicopter flies around in 3D rather than drives around in 2D. And so common way to model the state space helicopter would be to model it as having a position x, y, z. And then also a 3D orientation of a helicopter is usually modeled with three numbers, which we sometimes call the roll, pitch, and yaw, right? So, if you're in an airplane, roll is, are you rolling to the left or right? Pitch is, are you pitching up and down? And yaw is, are you facing north, south, east, or west, right? So this is one way to turn the three-dimensional orientation of an object, like an airplane or a helicopter, into three numbers. So the details aren't important. If you actually work on a helicopter, you need to figure this out. But for today's purposes, just, right, I guess the roll, pitch, yaw, right? But to represent the orientation of a three-dimensional object flying around is conventionally represented with three numbers, such as roll, pitch, and yaw. And then x dot, y dot, z dot, phi dot, theta dot, psi dot, right? The linear velocity and the angular velocity, okay? Maybe just one last example. So it turns out in reinforcement learning, maybe early history of reinforcement learning, one of the problems that a lot of people just happen to work on, and therefore you just see in a lot of reinforcement learning textbooks, is something called the inverted pendulum problem. But what that is a little toy, which is a little cart that's on wheels, that's on a track, and you have a little pole that is attached to this cart, and there's a free swivel there, right? And so this pole just flops over, or this pole just swings freely, and there's no motor. There's no motor at this little hinge there. And so the inverted pendulum problem is, see, look, I prepared this, right? Is, no, I have all these credits. If you have a free pole, and if this is your cart moving left and right, the inverted pendulum problem is, can you, with a free swivel, can you kind of balance that, right? Well, right. And so one of the sort of common textbook examples of reinforcement learning is, can you choose actions over time to move this left and right so as to keep the pole oriented upward, right? And so for a problem like this, if you have a linear rail, just a one-dimensional, like a railway track that this cart is on, the state space would be x, which is the position of the cart, theta, which is the orientation of the pole, as well as x dot and theta dot, right? So this would be four-dimensional state space for the inverted pendulum if it's like running left and right on a railway track, on a one-dimensional railway track, right? All right, cool. So for all of these problems, if you want to build, a self-driving car and have it do something, or build an autonomous helicopter and have it either hover stably or fly trajectory or keep the pole upright in an inverted pendulum. These are examples of robotics problems where you would model the state space as a continuous state space. So what I want to do today is focus on problems where the state space is Rn, so n-dimensional set of real numbers. And in these examples, I guess n would be 4 or 6 or 12, right? Oh, and again, for the mathematicians in this class, technically, angles are not real numbers because they wrap around, and they only go to 360 and then they wrap around to 0. But I think for the purposes of today, that's not important. So we'll just treat this as Rn. Oh, yeah. Okay. So, all right. So the most straightforward way to work with a continuous state space is discretization, where you might have, in this example, a two-dimensional state space, maybe a x and theta for the inverted pendulum, and then you just lay down a set of grid values, right, and discretize it back to a discrete state problem. And so, so you can give the states a set of names, 1, 2, 3, 4, whatever, and anywhere within that little square, you just pretend that your MDP, that your robot is in state number 1. So this takes a continuous state problem and turns it back to a discrete state problem. This is such a simple, straightforward way to do it. This is actually reasonable to do for small problems. And if you have a relatively small, low-dimensional state space MDP, like an inverted pendulum problem, 4-dimensional, it's actually perfectly fine to discretize the state space and solve it this way. Let me describe some disadvantages of discretization first, and then we'll chat a little bit about when you should just use discretization, because even though it's not the best algorithm, it works fine for smaller problems. But for bigger problems, we'll have to go to more sophisticated algorithms like fitted value iteration. Okay, but so what are the problems with discretization, right? Well, first, actually, I feel like these markers. This is a very, it's kind of a naive representation for V star and pi star, right? Which is, remember the very first problem we talked about of predicting housing prices? Imagine if X was the size of a house and the vertical axis was the price of a house, and you had a data set that looked like this, right? Discretization is, the discretization equivalent of trying to fit a function as data would be to look at the input feature and, let's discretize it into 5 values. And for each of these little buckets in each of these 5 intervals, let's fit a constant function, right? Or something like that, right? So this staircase would be how, discretization would represent the price of a house as a function of the size. And the analogy is that what we're doing in reinforcement learning is you want to approximate the value function. And if you were to discretize it, then on the x-axis is maybe the state. And now I'm down to one-dimensional state, right? Because that's what I can plot. And you're saying that, well, let's approximate the value function, as a staircase function, as a function of the set of states, right? And and this is not terrible. If you have a lot of data and very few input features, you can get away with this. This will work okay, but it doesn't seem to allow you to fit a smoother function, right? So that's one downside. It's just not a very good representation. And the second downside is the dimensionality. Right, somewhat fancifully named cursive dimensionality, which is, I think Richard Bellman had given this name. It's a cool sounding name, but what it means is that if the state spaces in Rn and discretize, each dimension into k values, then you get k to the n discrete states. Right? So if you discretize position and orientation into 10 values, which is quite small, then you end up with 10 to n states, which grows exponentially in the dimension of state space n. So discretization works fine if you have relatively low dimensional problems, like 2 dimensions, no problem. 4 dimensions, maybe is okay. But if you have very high dimensional state spaces, this is not a good representation. Right? And it turns out the curse of dimensionality, to take a slight aside from continuous state spaces, the curse of dimensionality also applies for very large discrete state MDPs. So for example, one of the places people have applied reinforcement learning is in factory optimization, right? So if you have a factory with 100 machines in a factory, and if every machine in the factory is doing something slightly different, then if you have 100 machines in a giant factory, each machine can be in k different states, then the total number of states of your factory is k to the power of 100, right? And so even if, so curse of dimensionality also applies to very large discrete state spaces, such as if you're a factory with 100 machines and then your total state space becomes k to the 100. And it turns out that for this type of discrete state space, fitted value iteration can be a much better algorithm as well. We'll get to fitted valuation a little bit. Okay. So let's see. So some practical. So now, despite all this criticism of discretization, if you have a small state space, is a simple method to try to apply. And if you have a very small state space, go ahead and discretize it. It could be one of the quick things to try and just get something working. So let me share with you some maybe guidelines. This is how I do it, I guess, right? If you have a 2-dimensional state space or 3-dimensional state space, is no problem. Just discretize. Usually, for a lot of problems, it's just fine. If you have maybe a 4 to 6-dimensional state space, I would think about it, and it will still often work. So for the inverted pendulum, which is 4-dimensional state space, it works just fine. I've had some friends work on trying to drive a bicycle, right, which you can model the 6-dimensional state space, and discretization, it kind of works. It works if you put some work into it. One of the tricks you want to use as you approach the 4 to 6-dimensional space range is choose your discretization more carefully. So for example, if the state S2 is really important, so if you think the actions you need to take or the value of the performance is really sensitive to the state S2 and less sensitive to the state S1, then in this range, people end up designing unequal discretizations where you might discretize S2 much more finely than S1, right? And the reason you do that is the number of states, the number of discrete states is now blowing up exponentially, some to the power 4, some to the power 6, and these tricks allow you to just reduce a little bit the number of discrete states you end up having to model. I think, if you have a 7, 8-dimensional problem, that's pushing it. That's when I would kind of be nervous and be increasingly inclined to not use discretization. I personally rarely use discretization for problems that are 8-dimensional. And then when your problems are even higher dimensional than this, like 9, 10 and higher, then I would very seriously consider an algorithm that does not discretize, right? Very rare to use discretization for problems this high. Even 7 and 8 is quite rare. I've seen it done in rare occasions, and these things get worse exponentially, right, with the number of dimensions. So maybe there's a set of guidelines for when to use discretization and when to seriously consider doing something else. Okay. All right. So in the alternative approach that you see today, what you'll be able to do is to approximate V star directly without resorting to discretization. Okay? And there'll be an analogy that we'll make later, just alluding to this plot again, right? To this analogy between linear regression, where you're trying to approximate y as a function of x, and value iteration, where you're trying to learn or approximate v as a function of s. Right? Maybe that's v star, I guess. Right? Which is that in linear regression, you say let's approximate x as a linear function of y, right? Or if you don't want to use the raw features y, what you can do is use theta transpose phi. Oh, I'm sorry, got that totally mixed up. Right, where phi of x is the features of x. So if right, so this is what linear regression does. Where if x is your housing price, then maybe phi of x is equal to x1, x2, x1 squared, x1, x2, and so on. Right. So that's how you can use linear regression to approximate the price of a house, either as a function of the raw features or as a function of some slightly more sophisticated, slightly more complex other features of the house. And what you'll see in fitted value iteration is a model where we will approximate V star of s as a linear function of features of the state. Okay, so that's the algorithm we'll build up to, and yeah, we're going to try to use linear regression with a lot of modifications to approximate the value function. Okay? And again, in reinforcement learning, in value iteration, your goal is to find a good approximation to the value function, because once you have that, you can then use the equation we had earlier to compute the optimal action for every state, right? So we just focus on computing the value function. Now, in order to derive the fitted value iteration algorithm, it turns out that fitted value iteration works best with a model, with a simulator of the MDP. So let me describe what that means and how you get a model, and then we'll talk about how you can actually implement the fitted value iteration algorithm and have it work on these types of problems. Okay. All right. So what a model of, or a simulator of your robot is just a function that takes as input a state, takes as input an action, and it outputs the next state S prime drawn from the state transition probabilities. Okay, and the way that a model is built is that the states and the actions are both, and let's see, and the way the model is built is the state is just a real value vector. Okay. Oh, and I think for simplicity, for now, let's assume that the action space is discrete. It turns out that for a lot of MDPs, the state space can be very high dimensional, and the action space is much lower dimensional than the state space. So for example, for a car, S is 6-dimensional, but the space of actions is just 2-dimensionals, right? The steering and braking. It turns out for a helicopter, the state space is 12-dimensional, And I guess most of you, I wouldn't expect you to know how a helicopter flies, but it turns out that you have four-dimensional actions in a helicopter. The way you fly a helicopter is there are two control sticks. So your left hand and your right hand, can move, has two dimensions of control. And for the inverted pendulum, I guess the state space is 4D and the action space is just 1D, right? Do you move left or right? So you actually see in a lot of reinforcement learning problems that it's quite common for the state space to be much higher dimensional than the action space. And so let's say for now that we do not want to discretize the state space because it's too high dimensional, but just for the sake of simplicity, let's say we discretize the action space for now, right? Which is usually much easier to do. But I think as we develop fitted value iteration as well, you get hints of when maybe you don't need to discretize the action space either. But let's just say we have a discrete action space for now. Okay. So all right. So how do you get a model, right? One way to build a model is to use a physics simulator. Right. So, in the case of an inverted pendulum, right, it turns out that if the action is what's the acceleration you apply to either positive or negative, or to the x or right, to the left or the right, then it turns out that let's see. So the state space is four-dimensional, right? And it turns out that if you sort of flip open a physics textbook using Newtonian mechanics, if you know the weight of the card, the weight of the pole, yeah, I think that's it actually. If you know the mass of the card and the mass of the pole, and the length of the pole, it turns out you can derive equations about what is the velocity, right? So it turns out s dot is equal, don't worry about this. Think of the math as decoration rather than something you need to learn. Where, L is the length of the pole, m is the mass of one of these things. I actually don't remember. M is the pole mass, A is the force extended, and so on. And a conventional physics textbook will kind of let you derive these equations, or rather than trying to derive this yourself using, either yourself using Newtonian mechanics or finding the help of a physicist friend, there are also a lot of open source physics simulator software packages where you can download an open source simulator, plug in the dimensions and mass and so on of your system, and then it'll spit out a simulator like this. It tells you how the state evolves from one time step to another time step, right? And so, so in this example, the simulator would say that S prime is equal to S plus, delta T times, I guess, times S dot, where delta T could be, let's say, 0.1 seconds. Right? So if you want to simulate this at 10 hertz, so that 10 updates per second, so that the time difference between the current state and the next state is 1/10 of a second, then you write a simulator like this. Okay, and really, the most common way to do this is not to actually derive the physics update equations. The most common way to do this is to just download one of the open source physics engines. Right? So this will work okay for problems like the inverted pendulum. I once used a physics engine to build a simulator for a four-legged robot and managed to use reinforcement learning to get a four-legged robot to walk around. Right. So it works, although the second way to get a model is to learn it from data. Right, and I personally end up using this much more often. So here's what I mean. So actually, let's say you want to build a controller for an autonomous helicopter, right? So maybe this is a case study, and what I'm describing is real. Like this will actually work, right? Let's say you want to build a, let's say you have a helicopter and you want to build an autonomous controller for it. What you can do is start your helicopter off in some state as 0, right? So with GPS, accelerometers, magnetic compass, you can just measure the position and orientation of the helicopter, and then have a human pilot fly the helicopter around. So the human pilot, using control sticks, will move the helicopter. They'll command the helicopter with some action A0, and then a tenth of a second later, the helicopter will get to some slightly different position and orientation, S1, and then the human pilot, will just keep on moving the control sticks, so you record down what action they're taking A1, and based on that, the helicopter will get to some new state S2, and then they will take some action A2, it'll get to some state S3, and so on. And let me just write this as S capital T, right? So in other words, what you do is take the helicopter out to the field and hire a human pilot to fly this thing for a while and record the position of the helicopter 10 times a second, and also record all the actions that the human pilot was taking on the control stick. Okay, and then do this not just one time, but do this m times. So let me use a superscript 1. Well, you get the idea. Right. To denote the first trajectory. So you do this a second time, right, and so on, and maybe do this m times. Right. So this is just a lot of math of saying fly the helicopter around, m times, right, and then record everything that happened. And now, your goal is to apply supervised learning to estimate ST plus 1 as a function of ST and AT, right? So the job of the model, the job of the simulator is to take as input the current state and the current action and tell you where the helicopter is going to go, like 0.1 seconds later. And so given all this data, what you can do is apply a supervised learning algorithm to predict, well, what is the next state S prime as a function of the current state in action, right? And the other notation is, when I drew the box for the simulator above, I was using S prime to denote ST plus 1 and S and A, right? So that's the mapping between the notations. And so if you use the linear regression version, of this idea, you will say, let's approximate ST plus 1 as a linear function of the previous state plus another linear function of the previous state. And it turns out this actually works okay for helicopters flying at slow speeds. This is actually not a terrible model if your helicopter is moving slowly and not flying upside down. If your helicopter is flying in a relatively level way and kind of at slow speeds, this model is not too bad. If you're flying a helicopter in a highly dynamic situation, it's flying very fast, making a very fast, aggressive turn, then this is not a great model, but this is actually okay for slow speed flight. And so I guess A here will be a n by n matrix because the state space is n-dimensional, so A is a square matrix, and B will usually be a tall, skinny matrix, I guess, whereas the dimension of B is the dimensional state space by the dimension of the action space, right? And so in order to fit the parameters A and B, you would minimize with respect to the parameters A and B of this. So you want to approximate st plus 1 as a function of that. And so, pretty natural to fit the parameters of this linear model in a way that minimizes the square difference between the left-hand side and the right-hand side. Wait, did I screw up? Yes. Go ahead. Say that again? Oh, sure. What's the difference between flying helicopter m times versus flying helicopter once? Very, very long. In this example, it makes no difference. Yeah, it's fine either way. Unless, yeah, for practical purposes, it doesn't matter. Sorry, for the purposes of this class, it doesn't matter. For practical purposes, if you fly the helicopter m times, it turns out the fuel burns down slowly, and so the weight of the helicopter changes slowly. And if you want to average over how much fuel do you have for wind conditions, this is what actually is done. But for the purposes of understanding this algorithm, flying it single time for a long time works just fine as well. Okay. So this is the linear regression version of this, and when we actually talk about some other models later called LQR and LQG, you see this linear regression version of a model as well. This is really just a linear model of the dynamics, right? We'll come back to linear models dynamics later next week, but it turns out that if you want to use a nonlinear model, plug in a nonlinear. If you can also plug in, right, phi of s, and maybe phi prime of a as well, if you want to have a nonlinear model. And this will work even better depending on your choice of features. Okay. Now, finally, having run this little linear regression thing, and it's not quite linear regression because A and B are matrices, but you can minimize this objective, and this turns out to be equivalent to running linear regression n times. So if S has 12 dimensions, this turns out to be equivalent to running linear regression n times to predict the first state, second state, third state, variable, and so on. Right? This is what this is equivalent to. But having done this, you now have a choice of two possible models. One model would be to just say, my model will set st plus 1 as ast plus bat. Another version would be to set st plus 1 equals ast plus bat plus epsilon t, where epsilon t is distributed. Maybe from a Gaussian density. Okay, and so this first model would be a deterministic model, and this model would be a stochastic model. Right, and if you use a stochastic model, then that's saying that when you're running your simulator, when you're running the model, every time you generate st plus 1, you would be sampling this epsilon from a Gaussian vector and adding it to the prediction of your linear model. And if you use a stochastic model, what that means is that if you simulate your helicopter flying around, your simulator will generate random noise that adds and subtract a little bit to the state space of the helicopter, as if there were little wind gusts blowing the helicopter around. Okay. And this is yeah, right. So, right. So in most cases, when you're building reinforcement learning models, and so the approach we're taking here, this is called model-based reinforcement learning, where you're going to build a model of your robot, and then let's train the reinforcement learning algorithm in the simulator, and then take the policy you learn, take the policy pi you learn in simulation, and apply it back on your real robot. Right? So this approach we're taking is called model-based RL. There's an alternative called model-free RL, which is you just run your reinforcement learning algorithm on the robot directly and let the robot dash the robot around and so on and let it learn. I think that in terms of robotics applications, I think model-based RL has been taking off faster. A lot of the most promising approaches are model-based RL because if you have a physical robot, you just can't afford to have a reinforcement learning algorithm dash your robot around for too long, or how many helicopters do you want to crash before your learning algorithm figures it out? Model-free RL works fine if you want to play video games, because if you're trying to get a computer, or play chess, or Othello, or Go, right? Because you have a perfect simulator for the video game, which is the video game itself. And so your RL algorithm can, I don't know, blow up hundreds of millions of times in a video game, and that's fine. But so for playing video games, or for playing traditional games, model-free approaches can work fine. But a lot of the successful applications of reinforcement learning to robots have been model-based. Although again, the field is evolving quickly, so there's very interesting work at the intersection of model-based and model-free that gets more complicated. But I would say if you want to use something tried and true, for a robotics problem, seriously consider using model-based RL, because you can then fly a helicopter in simulation, let it crash a million times, right? And no one's hurt. There's no physical damage anywhere in the world. It's just okay. And just one last tip. One of the things we learned building these reinforcement learning algorithms for a lot of robots is that, having run this model, you might ask, well, how do I choose the distribution for this noise, right? How do you model the distribution for the noise? One thing you could do is estimate it from data, but as a practical matter, what happens is, so long as you remember to inject, so let's see, it turns out if you use a deterministic simulator, a lot of reinforcement learning algorithms will learn a very brittle model that works in your simulator but doesn't actually work when you put it into your real robot, right? And so if you actually look on YouTube or Twitter, in the last year or two, there have been a lot of cool-looking videos of people using reinforcement learning to control various weirdly configured robots, right? Like a snake robot, or some five-legged thing, or some whatever. It's just cool, random. I'm not good at drawing this, but if you build a five-legged robot, I don't even know what has 5 legs, right? How do you control that? It turns out that if you have a deterministic simulator, using these methods, it's not that hard to generate a cool-looking video of your reinforcement learning algorithm supposedly controlling a 5-legged thing, or some crazy, a worm with 2 legs or something. So these crazy robots that you can build in a simulator. But it turns out that even though it's easy to, well, not easy, even though you can generate those types of videos in the deterministic simulator, if you use a deterministic model of a robot, and you ever actually try to build a physical robot, and you take that policy from your physics simulator to the real robot, the odds of it working on the real robot are quite low if you use a deterministic simulator, right? Because the problem with simulators is that your simulator is never 100% accurate, right? It's always just a little bit off. And one of the lessons we learned, the whole field learned, applying RL to a lot of robots, is that if you want your model-based RL work to work not just in simulation and generate a cool video, but you want it to actually work on a physical robot, like a physical helicopter that you own, that is really important to add some noise to your simulator. Because if the policy you learn is robust to a slightly stochastic simulator, then the odds of it generalizing to the real world, to the physical real world, is much higher than if you had a completely deterministic simulator. So I think whenever I'm building a robot, right, I pretty much, actually, yeah, I don't think with one exception, LQR, LQG we'll talk about next week, but with one very narrow exception, I pretty much never use deterministic simulators when working on robotic control problems, unless, assuming I want it to work in the real world as well, right? And again, tips and tricks. So the most important thing is to add some noise, and then sometimes the exact distribution of noise, go ahead and try to pick something realistic, but the exact distribution of noise actually matters less, I want to say, than just the fact of remembering to add some noise, right? Okay. By the way, you guys probably don't know this, but my PhD thesis was using reinforcement learning to fly helicopters. So I'm trying to, I don't know. So you're talking to someone that's crashed a bunch of helicopters and has model helicopters and has lived through the pain and the joys of seeing this stuff work or not work. All right, so now that you have built a model, built a simulator for your helicopter, for your four-legged robot, or for your car, how do you approximate the value function, right? So in order to apply fitted value iteration, the first step is to choose features of the state S, right? And then we'll approximate V of S, we'll approximate V star using a function V of S, which is going to be theta transpose phi of S. And so, I don't know, and so, in the case of in the case of a inverted pendulum, right? Then phi of S, maybe you have x dot, maybe you want x squared or x times x dot or x times the pole orientation, and so on. So take your state S and think up some nonlinear features, right? That you think might be useful for representing the value. And remember what the value is. The value of a state is your expected payoff from that state, expected sum of discounted rewards. So the value function captures if your robot starts off in this state, how well is it going to do if it starts here? So when you're designing features, pick a bunch of features that you think help convey how well is your robot doing. Does that make sense? And so maybe for the inverted pendulum, for example, if the pole is way over to the right, then maybe the pole will fall over. Or so give it a reward of -1 when the pole falls over, right? But so, sorry, I'm overloading notation a bit. Theta is both the angle of the pole as well as the parameters. But if the pole is falling way over, that looks like it's doing pretty badly, unless x dot is very large and positive, right? And so maybe there's an interaction between phi and x dot. So you might say, well, let me have a new feature, which is the angle of the pole multiplied by the velocity, right? Because then, because it seems like these two variables kind of depend on each other. So just as when you're trying to predict the price of a house, you would say, well, what are the most useful features predicting the price of a house? You would do something similar for fitted value iteration. And one nice thing about model-based RL is that model-based reinforcement learning is that once you have built a model, you see a little bit that you can collect an essentially infinite amount of data from your model, right? And so with a lot of data, you can usually afford to choose a larger number of features because you can generate a ton of data with which to fit this linear function. And so, you're usually not super constrained in terms of needing to be really careful not to choose too many features because of fear of overfitting. You could get so much data from a simulator that, you could usually make up quite a lot of features. And if some of the features end up not being useful, it's okay because you can get enough data from running your simulator for the algorithm to still fit a pretty good set of parameters data, even if you have a lot of features, because you can generate a lot of data to fit this function. Okay. So let's talk through the fitted value iteration algorithm. Let's see. All right. You know what? This is a long algorithm. Let me just use a fresh board for this. So let me just write down the original value iteration algorithm for discrete states. So what we had previously was we would update V of S according to R of S plus gamma max over A right? So this was what we had last Monday. And I said at the start of today's lecture that you can also write this as this. Okay, so let's take that and generalize it to fitted value iteration. All right. So first, let's choose a set of states randomly and let's initialize the parameters equals 0. Okay? And what we're going to do is so let's see, in linear regression, you learn a mapping from x to y, and you have a discrete set of examples for x, and you fit a function mapping from x to y. So in what we're going to do here, we're going to learn a mapping from S to V of S, and we are going to take a discrete set of examples for S and try to figure out what is V of S for them, and then fit a straight line, to try to model this relationship. Right? So just as you had a finite set of examples, a finite set of houses, like you see a certain set of values of X in your training set for predicting housing prices, we're going to see a certain set of states and then use that finite set of examples to use linear regression to fit V of S. Right? So that's what this initial sample is meant to do. And so this is the outermost loop of value iteration, a fitted value iteration. And then for I equals 1 through M, let's see. All right. So what we're going to do is go over each of these M states, go over each of these M states, right? And for each one of them, we're going to, and for each one of those states and for each one of those actions, we're going to take a sample of k things in order to estimate that expected value, right? And so this expectation is over S prime drawn from the state transition distribution. It's saying, from this state, if you take this action, wherever you get to next. And so these two loops, this for I equals 1 through M, and for each action A, this is just looping over every state and every action and taking k samples, sampling k examples of where you get to if you take an action A in a certain state S, right? And so And by taking that k examples and computing this average, QA, right, is your estimate of that expectation. Okay, so all we've done so far is take k samples, from this distribution of which S prime is drawn and average V of S. Oh, actually, I'm sorry. And if I move R of S inside, sorry, then that's Q of A. Yeah. Okay, does that make sense? Sorry, let me just rewrite this to move R of S inside. Fix this up a little bit. So this is written as gamma. Well, if you write this as max over A of R of S plus gamma, yeah, okay, yeah, sorry. So move the max and expectation out, then this is Q of A. Okay? Next, let's set yi equals max over A of Q of A. Right? And so by taking the max over A of Q of A, that's what yi is. It's your estimate of the right-hand side of value iteration. Right? And so yi is your estimate for this quantity, for the right-hand side of value iteration. Now, in the original value iteration algorithm, I'm just using VI to approximate that, to abbreviate value iteration. In the original algorithm, what we did was we set V of Si to be equal to Yi, right? That, in the original value iteration algorithm, we would compute the right-hand side, this purple thing, and then set V of S equals to that, right? Just set right-hand side equal to, set the left-hand side equal to the right-hand side. But in fitted value iteration, V of S is now approximated via a linear function, so you can't just go into a linear function and set the value of points individually. So what we're going to do instead is in fitted VI, we're going to use linear regression to make V of Si as close as possible to Yi. But V of Si is now represented as a linear function of the states, so a linear function of the features of the states. So V of Si is theta transpose phi of Si, and you want that to be close to Yi. And so the final step is run linear regression to choose the parameters theta that minimizes the squared error. Okay. Does that make sense? Okay. Oh, yes. I think just make my curly braces match, I think. Yeah, okay. Okay. So that's fitted. Oh, go ahead, question?
In the first step of the sampling, S bracket n, is that the same index as the trial that we ran when we ran n trials?
Oh, this one?
So this first one is,
Oh, this one? Oh, no. The M is used differently. So when we were learning a model, M was just how many times you fly the helicopter in order to build a model, and the number of times you fly the helicopter in order to build a physics model, to build a model of the helicopter dynamics it has nothing to do with this M, which is the number of states you use in order to sort of anchor or in order to so I think actually, so the way to think about this is you want to learn the mapping from states to V of S, and so this sample, this M states is we're going to choose M states on the x-axis, right? So and that M is the number of points you choose on the x-axis, and then in each iteration, a value iteration, we're going to go through this procedure. So you have sort of S1 up to Sm, right? And then for each of these, you're going to compute some value yi using this procedure, and then you fit a straight line to this sample of yi's.
yeah, that I understand. I guess I'm trying to map back to when we were doing the n trials. Is that each time a state?
Think of these, think of the way you build a model and the way you apply fitted value iteration as two completely separate operations. So you can have one team of 10 engineers fly the helicopter around, fly the helicopter around 1,000 times, build a model, run the linear regression, and then they have a model. And then they could publish the model on the internet, and a totally different team could download their model and do this, and the second team does not need to talk to the first team at all other than downloading the model off the internet. Right? Next question?
Do we do the sampling just because the model is not deterministic?
Oh, yes, good question. You mean the sampling k times, right? Yep, that's a great question. Yes, that was that was one of my next points, which is the reason you sample from this distribution is because you're using, so you should do this if you're using a stochastic simulator, right? And actually, this is actually what I was going to ask you guys. What should you do? How can you simplify this algorithm if you use a deterministic simulator instead of a stochastic simulator? Well, let's see. So if you use a deterministic simulator, then given a certain state and a certain action, it will always map to the exact same S prime, right? So how can you simplify the algorithm?
So in the for loop for each action, instead of drawing k samples, we only have to draw one sample.
Yeah, yep, cool, yep, great, yes. So if you're a deterministic simulator, you can set k equals 1 and set sample only once because this distribution, it always returns the same value. So all of these k samples will be exactly the same. So you might as well just do this once rather than k times. That make sense? Okay, cool. Yeah.
Just to clarify, the set QA, the thing with the square bracket is an expectation, right?
Oh, this one?
The segment is expectation.
Oh no, this is actually a square bracket. The thing is, we're trying to approximate this expectation, and the way you approximate the mean is you sample k times if you take the average, right? Right. So what we've done here is, in order to approximate this expectation, we're going to draw k samples and then sum over them and divide by k, so you average over the k samples. All right, cool. That's one question.
What is a good approximation for how many states we run in the sample, and then would we, after we run the whole value iteration, would we just try to run a different set of random S's to check how
let's see. So how do you choose M and how do you test the overfitting? So, once you have a model, one of the nice things about model-based RL is, let's say that phi of S, right? Let's say that phi of S has 50 features. Right? So let's say you chose 50 features to approximate the value function of your inverted pendulum system. Then we know that you know that you're going to be fitting linear regression, right, to this 50-dimensional state space. I mean, this step here, this is really linear regression, right? And so you can ask, if you want to run linear regression with 50 parameters, how many examples do you need to fit linear regression? And I would say, if M was maybe 500, right, maybe it'd be okay. You have 500 examples to fit 50 parameters. But if for computational reasons, if it doesn't run too slowly to even set M equals 1,000 or even 5,000, then there's no harm to letting M be bigger. So usually M, you might as well set to be as big as you feel like, subject to the program not taking too long to run, because if you're fitting, unlike supervised learning, if you're fitting data to housing prices, you need to go out and collect data, right, off Craigslist or Zillow or Trulia or Redfin or whatever, about prices of houses. And so data is expensive to collect in the real world. But once you have a model, you could set M equals 5,000 or 10,000 or 100,000, and then your algorithm will run more slowly. But so long as your algorithm doesn't run too slowly, there's no harm to setting M to be bigger. Does that make sense? All right, cool. So, so I know there's a lot going on in this algorithm, but this is fitted value iteration, and if you do this, you can get reasonable behavior on a lot of robots by choosing a good set of features and learning the value function to approximate the value of approximate the expected payoff of a robot starting off in different states. Okay. Now, just a few details to wrap up. Again, some practical aspects of how you do this. After you've learned all these parameters, you've now learned. Go ahead. Yeah.
In the value iteration, where are you getting the S prime J from? Is that from the parameters, or is that from the currently estimated data?
Oh, I see. Yes, thank you. Yes. So in this expression, where do you get V of S prime J from? Yes. So you would get this from theta transpose phi of S prime J using the parameters of theta from the last iteration of fitted value iteration. Yeah, just as in value iteration, this is the values from the last iteration that you use to update the new iteration. So then you use the last value of theta to update the new one. Yeah, thank you. Cool. Oh, and one other thing you could do, which is, I talked about the linear regression version of this algorithm, which is, this whole exercise is about generating a sample of S and Y, so you can apply linear regression to predict the value of Y from the values of S, right? But there's nothing in this algorithm that says you have to use linear regression. In order to, now that you've generated this data set, this box that I have here, this is linear regression, right? But you don't have to use linear regression. In modern, deep reinforcement learning, one of the ways to go from reinforcement learning to deep reinforcement learning is to just use a neural network for this step instead. Then you can then you call that deep reinforcement learning, where hey, it's legit, but you can also use locally weighted linear regression or whatever regression algorithm you want in order to estimate Y as a function of the state S. Yeah, and actually, if you use a neural network, it relieves the need to choose features phi as well. You can feed in the raw features, pore angle, pore orientation, and use a neural network to learn that mapping in a supervised learning way. Okay. All right. So one last important, I guess, practical implementational detail, which is fitted VI, right, gives approximation to V star, and this implicitly defines pi star, right? Because the definition for pi star is that oops, right? So when you're running a robot, you need to execute a policy pi, right? Given the state, you need to take an action. Given the state, you need to pick an action. And having computed V star, it only implicitly defines the optimal policy pi star, right? And so if you're running a robot in real time, then actually if you fly a helicopter, you might have to choose control actions at 10 hertz, meaning 10 times a second. You're given a state, you have to choose an action. If you're building a self-driving car, again, a 10 hertz controller would be pretty reasonable. I guess choose a new action maybe 10 times a second would be pretty reasonable. But how do you compute this expectation and this maximization 10 times per second? So in what we used for fitted value iteration, we used, right, a sample we use k examples to approximate the expectation. Right? But if you're running this in real time on a helicopter, probably you don't want to, at least, I don't know, for my robotics implementations, I have been reluctant to use a random number generator, right, in the inner loop of how we control a helicopter. Right? It might work, but I think, to approximate, if you want to compute this argmax, you need to approximate the expectation. And do you really want to be running a random number generator on a helicopter? And if you're really unlucky and a random number generator generates an unlucky value, will your helicopter do something, bad and crash? Or I would, again, just emotionally, I don't feel very good if your self-driving car has a random number generator in the loop of how it's choosing to drive. Right? So just as a practical matter, there are a couple of tricks that people often use, which is the simulator is often of this form. Right? Okay. So most simulators are of this form. Next state is equal to some function of the previous state in action plus some noise. And so one thing that is often done is for your deployment, or for the, for the actual policy you implement on the robot, set epsilon t equals 0, and set k equals 1, right? And so, this is a reasonable way to make this policy run on a helicopter, which is during training, you do want to add noise to the simulator because it causes a policy you learn to be much more robust to little errors in the simulator. Your simulator is always going to be a little bit off. Maybe it didn't quite simulate wind gusts, or when you turn the helicopter, does it bank exactly the right amount? The simulator is always, in practice, is always a little bit off. So it's important to have noise in the simulator in model-based RL. But when you're deploying this in a physical simulator, one thing you could do that would be very reasonable is just get rid of the noise and set k equals 1. And so what you would do is, let's see. Whenever you're in the state S, pick the action A according to argmax over A of V of S A, right? So this F is this F from here. So this is the simulator with the noise removed, okay? And so what you would do is actually, computers are now fast enough. You could do this 10 times a second, right? If you want to control a helicopter or self-driving car at 10 hertz, you can actually easily do this, at 10 times a second, which is your car or your helicopter is in some physical state in the world, so you know what is S. And so you can quickly, for every possible action A that you could take, use a simulator to simulate where your helicopter will go if you were to take that action. So go ahead and run your simulator, once for each possible action you could take, right? Computers are actually fast enough to do this in real time. And then for each of the possible next actions you could get to, compute V applied to that. So this is really, right, S prime drawn from PSA, but with deterministic simulator, right? Right? So every 10th of a second, you could, in your simulator, try out every single possible action. Use your simulator to figure out where you would go under every single possible action, and apply your value function to see, of all of these possible actions, which one gets my helicopter, in the next 1/10 of a second to the state that looks best according to the value function you've learned from fitted value iteration. And it turns out if you do this, then this is how you'd actually implement something that runs in real time. And I just mentioned, the idea of training with stochastic simulator and then just setting the noise to 0 is one of those things that's not very rigorously justified, but in practice, this works well. This question?
Isn't our action space continuous too?
Oh, yes. For the purpose of this, you can assume you have a discretized action space. And it turns out that for a self-driving car, it's actually okay to discretize the action space. For a helicopter, we tend not to discretize the action space, but it turns out if f is a continuous function, then you can use other methods as well, right? This is about optimizing over the, I didn't mean to talk about this, so sorry, this is getting a little bit deeper. But even if A was a continuous thing, you can actually use real-time optimization algorithms to very quickly try to optimize this function, even as a function of a continuous action A. There's a literature on something called model predictive control, which you can actually do these optimizations in real time and use it for a helicopter. Just one last question.
So once you take that action, you transition to the next state. So how do you know what next state you're in? Do you make an observation, or do you use the S prime that you
Wait, what's the question?
so once you're, like when you fly the helicopter, once you take an action, you'll transition to the next state. So do you make an observation to decide where you are, or do you use the S prime?
Oh, I use an observation. Yeah, yes. So you take an action, and then your helicopter will do something. There'll be some wind. Your model may be off, and so you would then, a 10th of a second later, take another, GPS reading, accelerometer reading, magnetic compass reading, and use the helicopter sensors to tell you where you actually are. No, cool. Okay, cool. All right. I hope, hopefully this was hopeful. I feel like, I think it's fascinating that the excitement about self-driving cars and flying cars and all that, it gets boiled down to equations like these. I think that's kind of cool. Okay, that's great. Thanks. I'll see you guys next week.